Preparing to live stream the meeting. Okay. Okay, we are live. Okay, so let me then go ahead and introduce George, and then he can start. Okay.
Okay.
Okay, so welcome to this plenary lecture in the second day of the Argentine Conference of Electronics 2021. Today we have the pleasure of having George Gielen, who received the Master in Science and PhD degrees in Electrical Engineering from the Catholic Universiteit in Leuven in Belgium in 1986 and 1990, respectively. He currently is full professor in the MICA's Research Division at the Department of Electrical Engineering at KU Leuven. From August 2013 until July 2017, he was also appointed at KU Leuven as Vice Rector for the Group of Sciences, Engineering and Technology, and he was also responsible for academic human resource management. He was visiting professor in UC Berkeley and Stanford University, and since 2020, he's chair of the Department of Electrical Engineering. His research interests are in the design of analog and mixed signal integrated circuits, and especially in analog and mixed signal CAD tools and design automation. He is a frequently invited speaker and lecturer and coordinator and partner of several industrial research projects in this area, including several European projects. He has more than 600 papers in edited books, international journals, and conference proceedings. He's a 1997 laureate of the Belgian Royal Academy of Science, Literature, and Arts in the discipline of engineering. He's fellow of the IEEE since 2002 and received the IEEE CAS Circuits and Systems Society Mark van Valkenburg Award in 2015 and the IEEE CAS Charles de Soer Award in 2020. He's an elected member of the Academia Europea. So, having said that, I leave you to George.
Okay, thank you, Pedro. Thank you, Benjamin, for this nice invitation to the Argentine Conference on Electronics. Hello, everyone. I would have loved to be there in Argentina, but you know the reason why at this moment this is not really possible. Now, I prepared my presentation here, which is about sensing interfacing in the edge. Small, sound, smart. Now, this is the abstract for later on, but for those of you who are in Argentina at the moment and don't know where Belgium is, I just copied here the map of the world. And so while you are here, I am here in this very northern part at the moment at Leuven University. Now, Leuven University, also called KU Leuven. K actually stands for Catholic, but internationally we speak of the University of Leuven. Here you see some pictures from our city. It dates back to the Middle Ages, and it has some beautiful Gothic buildings like our town hall and our library here that was built after the First World War. And this is a very interesting place here for students because this is our Grand Place, the central market square, which is sometimes called the largest open-air pub in the world. And this is where, in normal times, not in these pandemic times, our students spend a lot of their evenings. Now, our university is the largest in Belgium. It has in total 56,000 students, out of which 16% are international. So it's a very international oriented university. And the nice thing is that our city has only 100,000 inhabitants. Now you can imagine that on a city of 100,000 people with 56,000 students, that this completely changes the atmosphere of the city. It's very lively, very entertaining, at least during the months of the academic year. Again, at this moment, there's not much going on campus due to the pandemic. Okay, but back to the technical presentation. So I will talk about sensing and computation in the edge. I will start with a short introduction about what is the importance of sensing. And then I will talk about how we can make these sensing interface circuits, how we can make them small, how we can make them sound, and sound means robust, and how we can make them smart. And then I will finish with some conclusions. So today we find sensing sensors and sensor readout in many applications, and the number of applications is growing continuously. So we find sensing in automotive, industrial applications, in home applications, healthcare, consumer infrastructure, farming, etc. And so this amount of applications is increasing. And at the same time, we also see a trend towards a demand for smart sensing. And I will come back to that, what that means. Now, one big driver for this growth in sensing applications is the Internet of Things. So the Internet of Things is where we put sensing devices in our physical world. And all these sensing devices measure all kinds of signals and transmit the data to the cloud, to the internet, where they are being processed and used by other applications. And so this graph shows the expected growth of this Internet of Things. And you can see that it has a quite significant growth, which is actually on average something like 15.3% in this period. And if you know that the total growth of the semiconductor market in the same period is only something around 8%, then you know that IoT, Internet of Things, is a much bigger driver, a much bigger growth factor for the semiconductor industry than the overall market. And so this drives this need for sensing devices. Now, if you look at what money-wise, what business that is, then in 2019, we talk about something like $46,000 billion. And in 2025, this will be something like $114 billion. So that's huge numbers. And if you look at where this money goes, then you see that about 40% goes into software, applications, apps, processing software. Another 40% goes into the hardware of these devices, and there's about 20% that goes in the sensors itself. Now, what are the requirements for such sensing devices? Well, first of all, they must meet the performance. Secondly, many of these devices are powered up from some source, a battery, and of course, it's very difficult to impossible to replace these batteries continuously. And so low power, low energy consumption are key demands for these applications. Also, for many applications, cost is a very important issue. If the cost is not low enough, then the application itself might not materialize. People will find it too expensive. They will not buy it. They will not install it. And so it will not materialize. So therefore, the cost of these has to be low. And of course, when we talk about integrated circuits, the cost is related to the area of the device. So smaller area means cheaper solutions. A fourth requirement is that in many of these applications, we install them and they have to operate for a long period. So that means that they need to have a very high reliability and a very high robustness under all circumstances. Think of Industry 4.0. If we install it in a production environment, then the sensors must continue to work regardless of any dust, any changes in temperature, whatever, they must continue to work. So reliability and robustness are absolute requirements. And then in recent years, a very important fifth requirement is that there is a demand that the sensing devices become smart. Smart means that they do more than just collecting data. They should do processing of the data to some extent, and maybe use the processed data to take local action. I will come back to that later on. Now, to illustrate this with some examples, in our research group here in the university in Leuven, we have a large group of PhD researchers working on integrated circuits in many different application areas. And so I pick two results from my own students. One is about automotive resistive sensor readout. And you can see here from the picture that in cars today, the number of sensors that is being used is quite large. You have sensors to keep the car on the road. You have sensors for braking. You have sensors to control your seats, etc. So many sensors. And the challenge is to make them cheap and to make them such that their price goes down year after year. And here we built an alternative solution for such a sensor readout chip that is achieving 16.1 bit of resolution by exploiting second and third order noise shaping. And the nice thing is that the area of the chip is quite small, and therefore the cost is quite low. How we do that, I will explain later on. Another application from another PhD student, Carolina Mora Lopez, is shown here. It's a biomedical application. The idea is that we built a neural recording and stimulation system to measure the signals in the brain and then create a closed loop system in order to stimulate locally the brain. A typical example could be, for instance, the control of attacks of epileptic people. So people with epilepsy, when they get a seizure, the brain probe that is put in the brain at the right place can detect whether a seizure is in the phase of being developed. And then this information can be processed, and then a local stimulation can be given such that the actual attack will not occur. So the attack is then prevented by this built-in closed-loop system. Of course, when we do experiments, we build the chips on silicon, but the experiments are done on mice or on rats. Here I show you some early results that we developed. So this is the entire probe, entirely on silicon. So this is the electronics, and this is the probe shaft here. And in the probe shaft, as you can see, this is a zoom out, you see all the different electrodes. And so we stick this into the brain, and the electrodes, when they are close to the neurons, they can record the signals of the neurons, or if you stimulate, you can stimulate the neurons in the neighborhood of the electrodes. And then the readout electronics, so that is this then in a zoom out, you see that we can read out many channels in parallel. And of course, when you read out small signals from the neurons, the operations that you need to apply to the signal are you need to amplify, you need to filter, and you need to digitize the signal. And all that is here. So we have in every channel some amplification, some filtering, and then here we have the A to D converters. In this early chip, we were able to read out 455 electrodes, and at any moment in time, we could pick 52 and read them out in parallel. So we could not read out all 455, but pick out 52. And we also had 13 stimulation electrodes. And the unfortunate thing is that the power consumption was 17.8 microwatt per channel. So since then, there has been a pressure and further research done by us to do two things. One is to increase the number of electrodes so that we can have more contacts with the neighboring electrodes. And secondly, try to reduce the power consumption per channel. If we are able to reduce the area of these devices, then we can put more on a chip and therefore can read out more channels. But at the same time, also other applications are possible. And here I show an example. Assume that we could make A to D converters. If we could make A to D converters so small that we can put them in a 3D stacked way underneath an imager. So we have an imager array with the different pixels. We put the A to D converters underneath, and then we could have a pixel-wise readout of the imagers, and this would immensely improve our capabilities because it would decouple the resolution of the imager from the signal to noise ratio and from the frame rate. So resolution, accuracy, and speed would be decoupled if we were able to do this. And then we could build interesting applications. For instance, we could build artificial flying insects. Insects that could monitor things, that could be helpful in farming applications and all that. So I hope to have set the stage, showed the importance of sensing. And now I will explain how we can proceed to make these sensor interfaces small. Now, sensor signals are analog, so that means that to some extent we need analog circuits to read out these sensor signals. But analog circuits in general are not small. And the question is, why are they not small? Well, the answer is because of the physics of semiconductors. We have, on the one hand, we have thermal noise in our circuits, and we know from the papers from Professor Vitos that the power needed for analog signal processing is proportional to the bandwidth of the application and proportional to the square of the dynamic range. So power increases with bandwidth and the required accuracy. And this is because of thermal noise. But at the same time, we also know from many publications published by authors like Peter Kinget that also due to mismatch of analog devices, mismatch of transistors, mismatch of capacitors, we have a similar relationship that the power is proportional to the bandwidth and to the dynamic range squared. So it means it's a very similar relationship, only with some different coefficients of proportionality. And therefore, in general, we can say that the power in analog circuit depends on the speed or the bandwidth that you want and depends on the square of the accuracy. As long as we want a certain speed and a certain accuracy, that's the power that we consume. And why is it that these three are related? It is because of the area. So if you want a certain accuracy, then mismatch or noise tell you to use a certain area. Otherwise, you will not be able to meet that accuracy constraint. And so for that given area, for a given power, you have a certain speed. If you want to increase the speed, you need more power. So the area is linking these three power, speed, accuracy together. And that is why for a given application, we are not very able to reduce the area of our analog circuits. Now, I told you that in these IoT applications and also in applications like automotive and so on, there is a continuous drive to reduce the costs and therefore to reduce the area. And I now tell you that it's going to be very difficult to do that in the traditional analog way. So how can we solve that problem? Well, you have to think differently. And the way out that we found is to not implement the analog circuits in a traditional way, but to implement them in a highly digital way. So not in traditional analog way, but in a highly digital way. Now, traditional analog implementation processes the signals in the voltage domain. So a signal is represented by voltage, and that voltage is then amplified, filtered, digitized, etc. This makes that it's very difficult to make the circuits smaller, and it also gets under pressure when the supply voltage of the CMOS technology, the CMOS technologies, when that supply voltage is shrinking. And so we said, no, we have to do it differently. How? Well, by processing the signal information, not as a voltage, but in the time domain. So we represent the signal as some time. This could be a frequency, for instance. And so representing the sensor information as time or frequency and then digitize it is the alternative to processing through voltage. So how can we do that? How can we convert an analog signal, a physical signal, into time or frequency signal? Well, this could be done by using a ring oscillator. So a ring oscillator is nothing else than a ring of inverting stages, as you see here. And if somehow we can influence the frequency of oscillation of this ring oscillator with the physical sensor signal, then we can have a controllable oscillator controlled by the sensor. For instance, let's take the example of a capacitive sensor. If we have a capacitive sensor as shown here, where the value of the capacitance is changing with the signal that you are sensing, think of a pressure sensor, but you can also think of a sensor on an electronic skin, where you measure the pressure based on touching some object. But you can also think of an accelerometer as used in cars, etc. Such a capacitive sensor has a capacitance value that changes with the signal that you're sensing, and therefore the capacitance value changes, the load in the ring oscillator changes, and therefore the frequency of oscillation changes depending on the value of the physical signal that you are sensing. So this is how you can convert physical signal through the sensor into a frequency or a change of frequency. Now, how do you read that out digitally? Well, the basic principle is shown here. Let me clean the slide here. So the basic principle is I copy the same oscillator a second time as shown here. But now instead of adding the sensor signal, the sensor capacitance, I'm adding a bunch of capacitors that are controlled by switches. So they are digitally controlled. And I put the two oscillators in a loop controlled by a phase detector. The phase detector does nothing else than comparing the phases of the two oscillators and producing an output that is proportional to the phase difference. Now, because this is a negative feedback loop, it will reach equilibrium when the phases of the two oscillators are the same. Therefore, it will reach equilibrium when the two run at the same frequency. Now, because this oscillator's frequency is controlled by this digital control here, that controls the switches. And if the two oscillators run at the same frequency, it means that in the end, this digital output is a digital version of the analog signal that controls this capacitor here, the sensing capacitor. So we have a digital output that is a digitized version of the physical analog signal. Okay, so that's the basic principle. How can we look into this? What are the features? Well, the nice thing is that if you look at these features, after circuit, what do I need? What kind of circuits do you need? You need one ring oscillator, a second ring oscillator, and a phase detector. So all these are highly digital circuits. So that means that I can now build an interface, a sensor readout circuit that has an analog functionality, but that is built with circuits that are digital in nature. And as a result, they have a very small area and they are very scalable when you move to a more advanced semiconductor technology. Second feature of this structure is that we have two identical ring oscillators. And so as long as there is some change in the environment that affects the two oscillators in the same way, it doesn't change the output. So it means that the circuit is very robust to anything that is a common mode variation, a common mode error. For instance, a change in temperature. Doesn't matter as long as the two have the same temperature change. So it's a very robust structure. And then as a third feature, and that's maybe the most surprising one, is that this looks very similar to a delta sigma converter. You know that in a delta sigma converter, we have a delta and a sigma. So the delta takes a difference. Well, the difference here is taken here in the phase detector. So that's the delta. And then there must be a sigma summation, an integration. And in this case, the integration is done here in the oscillator because the voltage controls the frequency and the phase is the integral of the frequency. So there is an implicit integration in these controlled oscillators. So that means that I have a loop with a delta, a difference operation, and I have an integration. Therefore, I have a delta sigma functionality. And that means that if I am using oversampling to read out the output, then I have first order noise shaping inherently, implicitly in this structure. Comes from for free from this structure. And of course, with oversampling, you can improve the resolution of your circuits. So adding more oversampling improves the resolution. And for sensing applications, this can be done quite easily because sensors have sensing applications typically have a bandwidth that is quite low. So this may be 1 kilohertz or 5 kilohertz or 10 kilohertz or 20 kilohertz, but that is the bandwidth. So with some megahertz of frequency, you already have a lot of oversampling in the structure, and therefore you can improve your resolution. Now, if that is the case, so where is then the limit? So what is limiting the performance? Well, as always, it then becomes the noise. And in the case of an oscillator, the noise shows itself as phase noise or jitter in the oscillators. So that means that if your oversampling is high enough, ultimately you are limited by the phase noise of the oscillators. And that is what is shown here on this plot, where I show the signal to noise ratio that is achievable as a function of the phase noise of the oscillators. And so for low phase noise, you reach flat level that depends on the amount of oversampling. So if you look at this color here, this light blue, this is an oversampling ratio of 50. If you look at the green one, it is an oversampling ratio of 500. So the more you oversample, the higher this level for low phase noise values. And then for high phase noise values, the signal to noise ratio is limited by the phase noise or jitter. Okay, so that's what is the trade-off in the structure. And so you have to design your oscillators well enough that they have a phase noise that is just low enough so that the quantization noise level and the phase noise are about equal. Using this basic principle, we have then built several circuits to demonstrate this. And here is an example for a capacitive sensor readout using this time-based principle with a multi-bit phase detector and then the feedback here and then two identical oscillators. And the nice thing is that this circuit was done in 28 nanometer technology, and we operated it at as low a supply voltage as the digital circuits, as the ring oscillators were able to operate. And as a result, because of this highly digital structure, the total area was quite low, and therefore the cost was quite low. So conclusion here is that in this way, using time-based implementations for the analog interfaces that are highly digital, but still with analog functionality, you get an active area that is quite low. Now, the same principle can also be applied to resistive sensors, but of course you have to change a bit the architecture. And so that is shown here. Let's assume that we have differential resistors. We put them in a Wheatstone bridge kind of configuration. And in the other branch, we put resistors that are digitally controlled. Again, with switches, you can change the value of the resistor. The control signals for the switches come from the output of the circuit. And then you use the two tap points, the mid tap points here of the two branches of this Wheatstone bridge, and you feed it to a VCO. One controlled here by the sensor branch, the other controlled by the digitally controlled branch. Again, you compare the phases, you add some digital filtering, and then you feed it back. The loop does the same thing. It tries to balance the two midpoints. So the digital output is the one that balances the 2 points. So the frequencies of the two oscillators are the same. Since one is influenced by the sensor signal, the other one is the digital representation of that sensor signal. In this case, because of the extra filter that we add here, you get a second order noise shaping structure. And again, it's very small in area and technology scalable. And this was at that time implemented in a standard sensing technology, which is 130 nanometer. Okay, so these were two chips that we designed in order to demonstrate that with this concept, you can build for kind of any type of sensor, a highly digital type of readout circuit that is very small in area and technology scalable. Now, we then also investigated the power consumption, and the power consumption was not bad. It was equally good to the state-of-the-art voltage mode solutions, but it was not better than the voltage mode solutions in terms of power. It was better in terms of area. So we then investigated what we could do in order to further improve the power consumption. And we said, okay, we will investigate the use of nanotechnologies beyond CMOS. And we started the collaboration with Stanford University, and we explored the capabilities of carbon nanotubes, CNTs. And the reason why we investigated the use of CNT technology is because carbon nanotube transistors have an energy delay product that is predicted to be more than 10 times better than CMOS technologies. And therefore, if the energy delay product is 10 times better, we also expect that implementations of highly digital circuits in these technologies, that they also result in a much reduced power consumption compared to the CMOS implementations. Okay, and so using the Stanford carbon nanotube technology, we implemented a couple of sensor readout circuits using the same ring oscillator based concepts that I presented before. And here you see how we can read out infrared signals. The circuits we need are highly digital. Therefore, implementing them in CNT technology was not any difficulty at all. And the nice thing is that you even don't need, for many applications, you don't need a separate sensor. For instance, for infrared, we know that carbon nanotubes are sensitive to infrared. So we don't need a separate sensor. The CNT circuit itself, the carbon nanotube circuit, becomes the sensor. You just make sure it's exposed to the infrared light. Infrared light comes in, and then it changes the characteristics of the ring oscillators, and therefore you can read out that change. Of course, you have to make sure that the second ring oscillator is covered. Otherwise, you don't measure anything. And so we did. And so this entire circuit worked directly as an infrared sensor. It was built in a 32 nanometer Stanford CNT technology. And the nice thing is that indeed, as predicted, the power consumption of this technology was very low. So this circuit only took 130 nanowatts. So if I summarize the conclusions from this part, how can we achieve ultra miniaturization? Our solution was to implement the circuits in a digital-like way. So try to avoid implementing analog circuits in an analog way. Secondly, you can exploit oversampling, averaging, and so on in order to improve performance. The adoption of advanced technologies like carbon nanotubes helps to get a better performance. And as I said, you can also use the stacking in order to further enable some applications. And something that I did not mention is that you can also exploit the system level. So rather than trying to build very accurate individual sensing devices, maybe the individual devices don't have to be accurate, but if you have enough of them and you combine the information, maybe the overall system becomes accurate. So that's another way of thinking to get to the accuracy, but at your system application level. Now I move on to the second part, is how to make the sensing sound. Well, you know that this is the basic structure we have for a resistive sensor readout. And the challenge is that I assumed a few things. One is that I assumed that these oscillators are identical. In reality, we know that there is mismatch, so they are not identical. Temperature varies a lot. The aging of the circuit may occur and so on. And so we have to make this type of digital oriented interface, we have to make it robust or resilient. So how did we do it? Well, we investigated this resistive sensor readout as a test case, and we worked in 3 steps. First, we looked for a way to make sure that our digital output was temperature stable. To do that, we replaced the digitally controlled resistors that we had in the previous slide. We replaced them, so we put the 2 sensor resistors at the bottom, and we drive them with current sources. Current sources means with a current steering digital to analog converter. And again, they are steered from the digital output of the circuit. The rest of the circuit is the same. We have 2 oscillators, we have a phase detector, and we have some digital filtering. So that's the same structure. But by using the driving the bridge with current sources, we found that the change in resistance due to the sensor signal relative to the nominal value of the bridge resistors is given by the LSB current of the DAC over the nominal current times the digital output. And we know that this is a very temperature stable ratio, the LSB value over the nominal value in this DAC. So that guarantees us a very temperature stable readout. Second thing is the mismatch of these two oscillators. In reality, even if you copy the layout, because of the production variations, stochastic production variations, they will never have the same frequency and they will never have the same conversion gain. There will always be mismatch between that. And so that will have an impact on the output. Now, in a traditional amplifier, when you have such offsets, what you do is you do chopping. Well, we do exactly the same thing, but in this case, the chopping is done not on the amplitude. The chopping is done in the time domain. So it's time-based chopping, meaning that we interchange the position of the oscillators in this readout chain. And we do the same correction afterwards. Now we found that if you do this time-based chopping, then you can remove to some extent the errors due to a mismatch in frequency, offset frequency, and a mismatch in conversion gain, but not completely. If these two errors occur at the same time, then chopping alone does not solve these two problems. It does solve, though, the low frequency 1/f noise. So it reduces the impact of 1/f noise. So chopping is certainly needed, but it's not sufficient. And that's why we added a third correction, and that is a tuning. So both oscillators can be tuned. And so with the tuning, we are able to make sure that their free running frequencies are the same. And by doing so, we correct one of the two error sources that I mentioned, and then the chopping will resolve the other one. And that is what you see here. If there is any difference between the two oscillators with the tuning, we can reduce the difference to 0. And then on the red curve, you can see that we go to an accuracy that is very high again. And the nice thing is that this tuning can be done completely on chip, and you don't need any accurate reference nor any external components in order to do that. So with these three techniques, the current steering, the chopping, and the tuning, we were able to build very accurate circuits. And that is shown here. The prototype circuit achieves 15 effective bits. And as you can see here on this spectrum plot, without chopping and tuning, you have a lot of 1/f noise that disappears with the chopping, but you still have this problem here. And so by adding the tuning, you also reduce that and you get this very good resolution. And this shows that indeed the behavior of the circuit is nice across the entire temperature range. For automotive applications, for instance, we measured completely from -40 degrees centigrade to 175 degrees centigrade. And you see that without this chopping and tuning, you have a high error. And then with chopping and tuning, you have an error that is very small, close to 0. So you can see that the drift across temperature is below 0.3 ppm and 2.3 ppm per degree centigrade. So very low drift values. And this over the entire automotive temperature range. So that was quite an achievement that we were able to demonstrate that this type of time-based circuits can do the same thing as traditional voltage-based. Now this brings me to the last part, is how do we make the sensing smart? I told you that we put the sensors in the physical world, and then they collected data, and in a traditional way they were transmitting all the data to the cloud where they were processed, and then the data would come, other data would come back, and then you could actuate locally. Now, transmitting a lot of data through the cloud with this increasing number of sensing devices, that's a lot of power that is wasted. The amount of data is huge, and secondly, a lot of these data do not contain any information. And so that's why people today, they want that there is computing done in the edge. So in the edge device, in the sensing device, there must be some computing done so that less data and only relevant data are transmitted to the cloud. And so if you want to do this, you need edge circuits where you can adapt dynamically the performance. And we're also looking for edge circuits that are smart, that are inspired by nature. And that means that we look for only sampling the signal when there is information, and that we only sample relevant information. And finally, when you do local processing, you can also think of putting some learning capability in the edge device. So I will illustrate this in the following slides. So the first concept is instead of transmitting the raw data to the cloud, you can do local compression, local processing to reduce the amount of data. And an example was given here from the group at EPFL with the biomedical data from the electrocardiogram. So this is the well-known signal. But with some mathematical techniques, some compression techniques, you can reduce the amount of data that is in this ECG signal down to 8%, transmit that 8% of data, and then on the receive side, you can build up the original signal again without significant loss of information. So that means that instead of transmitting 100%, you only have to transmit 8% and still have the same information. Obviously, that will reduce the power consumption quite a lot. Another technique that we have been using is to not sample the signal in a digital way all the time, but to use signal-dependent processing. For instance, what I use here as illustration is signals from the brain. And we know that in the brain we have the action, so we have the lobe field potentials, which is kind of the background signal in the brain. And then on top of that, there are some nearby neurons that fire, and they are called the action potentials. And they are the spikes that you see here. So these are the neurons that fire. And it's clear that for most applications, you're not really interested in this background signal, but you're interested in when there is a neuron that fires and which neuron is it. So that means that there is only useful information when there is really a spike and not when there is a small background signal. And so instead of using an A to D converter that has a linear scale and that treats small signals in the same way as large signals, for this kind of application, we could build an A to D converter that has a higher resolution for the large signals, so for the spikes, and that has a low resolution for the low signals, which is the background signal, which is of no interest for most applications. And so that means that you have nonlinear A to D converter characteristic, but that is targeted for your application. And we built such a device and we made it programmable through a DAC with 10 bits, as you can see here. A third concept that we applied to make the sensor interface smart is to use event-based sensing. Again, I take the neural example, measuring neural signals. When there are spikes, that's of interest for the application. But when there are no spikes in the application where that is not relevant, we don't need to sample that non-relevant signal. So it's only important that we really sample at the moments given by the spikes. So that means that we have to build circuits that are triggered by an event, that are triggered by a spike, and in between they go in a kind of sleep mode, a low power sleep mode. And so we have been exploring the concept of asynchronous sampling. So not sampling with the clock, but sampling really when the signal changes enough. And we published last year a paper that shows that depending on the kind of application, be it cardiogram, muscle signal, EMG, action potentials, or EEG, that depending on that, you can have a lot of power savings between a standard SAR A to D converter, successive approximation A to D converter, and this new type of asynchronous sampling devices. So the yellow is a fully asynchronous solution, and you can see that there is a huge power saving possible between this and the standard way of digitization. The same for other applications, but the reduction may not be as significant. So this plot really shows that the benefit really depends on the type of application. So whether you're EEG or EMG, it has an impact on whether you can gain in these applications or not with this type of asynchronous techniques like a level crossing A to D converter. And then a last element is this learning component. So once we can do this processing in the edge and we try to locally extract the relevant information, we can also feed this information to a neural network. We can train the neural network to interpret the data and to use then that interpreted result to take action. And a typical example is shown here. So this is, for instance, the image of a camera on a drone. And then we could digitize all the pixels and so on. But what we try to do now is to extract real time in the drone or in a car or in a bike or whatever, to extract objects like a car or a pedestrian or a trailer that is being parked, etc. Try to get from the image data, get the features and use those features as input to the neural network that then decides, oh, this is very likely a pedestrian, this is a car that you see and so on. And then this is then used for the drone to navigate around in a fully independent way. And the challenge, of course, is to build hardware to do this feature extraction and to do this neural network processing, to build hardware to do that efficiently in an edge device. So this brings me to the conclusions. I hope to have convinced you that network sensing has become ubiquitous in many applications with Internet of Things and personalized medicine key drivers. That for these we need miniaturized sensor interfaces. And the way how we found to miniaturize these, to make them small, is to use highly digital architectures. And I've also shown you how we can increase the efficiency. I have shown you how we can build these interfaces such that they are extremely reliable under different operating conditions, and how we can build intelligence into these edge devices so that they extract locally information, they can adapt to the data, to the environment that they receive. And then I repeat that intelligence might also be built at the system level, even though the individual nodes can be quite simple. I conclude by thanking my PhD researchers who did all this work, my collaborators from KU Leuven and other universities, and my funding organizations. And if you have any questions, I'm happy to answer at the moment. And if you have a question later on, you can mail me at this email address. Thank you very much. And now I'm open for any questions.
Okay, thank you, George, for that great presentation. And thank you for taking the time and doing it. It's 10 p.m. in Europe, so thank you so much for this effort. I have a couple of questions while the other guys think and check on the YouTube channels if there are more. My two questions were, first one, the process you mentioned with the carbon nanotubes. If I understood correctly, the carbon nanotubes were used for building the transistors. So what kind of process was that? How big the devices were, and whether this was something that could be scaled commercially or just prototype? And the second question was, in that example that you showed, where you had the two VCOs that form like a delta sigma, if you try to do like applying a filter and doing second order, the third order structures.
Yeah, so about the technology, this was the experimental technology when we did this work several years ago, was experimental technology from Stanford University. And they built a carbon nanotube transistor by having carbon nanotubes like this, diameter about 1.2 nanometer. And you have to build many of them in parallel. And then you connect them in parallel at the source, and you connect them in parallel at the drain, and you put a gate on top. Now, why do you need to put many in parallel? Is because when you fabricate them, you don't know in advance whether they are metallic or semiconducting. So what they do is they just put many of them in parallel. You put a voltage at the bottom, so you turn them on, and those that are metallic, they burn themselves. And then you have enough left over to still create a transistor. This is a VLSI compatible technology, meaning that you grow the carbon nanotubes first on a separate substrate, then you transfer it to a wafer, and then you can do all the standard extra processing steps, putting the sources, putting the gate on top at wafer level. So that's very interesting. And secondly, about scaling, the scaling of the length of the devices is a photolithography. So it can follow a similar lithographic scaling procedure as standard CMOS technology. And that is also shown here, is that the ones we were using in our last infrared sensing device was 32 nanometer CNT. and this could go to 16 nanometer and so on if you have the lithographic tools to do that. Now, because it's VLSI compatible, this technology was later on further developed by Stanford and very recently has been transferred to a commercial foundry. I think it was SkyWater that has adopted this technology. And so at this moment or very soon, there is a commercially available version of this kind of technology available with scaling possibilities. Then to answer your other question, if I clear out. So indeed, the integrator is implicit in the sense that that's a first order. The delta is here, but by putting extra filters in the loop, you can build second order or third order systems. And so there have been publications where they have, with this kind of concept, built second or third order noise shaping. One order is implicit in the VCOs, and the two other orders are by extra digital steps. And then, of course, with oversampling, you have higher noise shaping, therefore you can reach higher resolutions. And if I go back to the example in the beginning here, this was a result that we published last year. And this chip has, let me first clean out here, has second and third order noise shaping. So it has the same concept, but with second order and third order noise shaping. And as a result, remember the other one was 15 bits. As a result, this one can achieve 16.1 bits of resolution. So that's all possible, and it only requires extra digital circuits. So that's very small and very scalable.
That's very interesting.
Yeah.
Very interesting.
Pedro?
Yep.
Yeah, we have a question here on the chat from YouTube. Maximiliano said he was very impressed with cognitive sensing. He asked which of these technologies are used today in devices such as Tesla cars and drones.
Sorry, can you about what the
about the cognitive sensing?
Okay,
so,
yeah.
He asked about the current applications on devices like cars.
Well, so I think especially autonomous systems, they have this kind of technology on board because you cannot transmit all the data to a central controller who would then steer the drone or the car. So the processing and the decisions have to be done on the device itself. Now the drawbacks or the challenges of this system is that, of course, object recognition and any neural network today is never 100% correct. I mean, you detect 96%, 97%, but you make a few things. So that's why on any real application, you will also have alternative sensors, maybe a camera, maybe a radar, different signals, and you will do a sensor fusion. You will a fusion of the data of these in order to improve the accuracy of your decision level of your autonomous vehicle.
Makes sense. A question from me is when you talk about a synchronous ADC triggered by events, how you think is do you think can you miss some information useful that previous to the event that triggers the sampling, or what is the strategy for that?
No, I don't. I don't think that the asynchronous sampling, you have to see it as the A to D converter itself is sleeping, and it's triggered if the signal changes. So if nothing happens on the signal, or the signal stays below a certain level, the A to D converter sleeps on. But as soon as the signal does something, then the A to D converter ramps up and does the conversion. So in principle, it does not miss any events, but it saves a lot of power, because most of the time in these applications it's just in sleep mode. And then it depends on what you do with those asynchronous data. But if you can do the training, let's think about this cognitive sensing. If you can do the training of the neural network is a spike-based asynchronous thing, and you feed your asynchronous data to that, then you save a lot of power in the overall system.
Yeah, makes sense. So according to the applications, the SAR-ADC comparison with the others, the other topologies become much better. Is mainly because they are smart for the application, or
Yes.
in general terms they are more efficient?
No.
It's just
the reason why smart systems are smart is exactly because they exploit features of the application. So if you don't know anything about the application and you have to anticipate that any signal is possible, then the best thing you can do is just digitize it in a standard way at a rate that is high enough, and then you can use a SAR because it's the most energy efficient. But if you know something about your application, like you know that the brain signals are like this and then a spike once in a while, then you can do better. So all these techniques can do better, but application specific.
Yeah, totally makes sense. Okay. Pedro, last question or from the chat?
Okay, I was muted. One last question.
Okay.
So if you had, could you comment on the trade-offs if you had to choose whether to go up in the frequency or go up in the order of the shaping filter in these examples that you showed? What way would you choose?
What we try to do is to increase the order and try to keep the frequency as low as possible, such that it's still sufficient in order to meet your quantization noise due to the oversampling. Because you may not forget that your oscillators must run at those frequencies. So the higher you put those frequencies, the more switchings you do, so the more power is consumed there. So you try to run them as low as possible, and you can decrease that frequency by increasing the order.
Increasing the area. Okay.
And that's digital. So yeah. Extra
it's
digital.
Convenient.
Yeah.
Okay. I'm done. I don't know if you guys have any more questions.
From chat, they thanks George for the interesting talk, and they think how much advanced is the compressive sensing technology if the reconstruction processing time allows today to make real-time applications.
It depends. I think at this moment they are not so much looking for real-time applications. you can transmit the data and do the reconstruction and then present that to a doctor or something offline. I don't think that if you really want to build a real-time system, then you better put the electrodes on the baby and then connect it to the machine there. And I wouldn't go through the cloud for that.
Yeah. Okay. We are good, I think, Pedro. So. Okay,
George. So thank you very much for this very entertaining and inspiring talk. Thank you from all the guys in this Argentinian Conference of Electronics, and we hope that in one of the coming years we can have you physically there once we get rid of this pandemic.
Yeah, I hope so too. Yes.
Okay. Thank you so much, George. Thank you, really.
Thank you very much, George.
Okay. Thank you very much for the invitation, and let's hope we'll see each other soon.
Yep.
Yeah.
Yeah.
That's good. Thank you a lot.
Thank you.
Bye-bye.
Bye.
Bye.